You're 1 minute away. It's the Infinity presentation.
Okay, so thank you guys for coming out. It's really awesome that we're able to co-host an event with the Toronto chapter of AES, the Professional Society, not the student chapter, obviously. They were able to get us 2 great presenters from Shure, Snyder, who's a corporate archivist, and Jason Cillo, who is a senior acoustical engineer. And they have prepared 2 presentations. They're going to be 30 minutes roughly each, with 15 minutes of questions in between. And we also have a message from Alan Clayton, who helped put this together.
Good evening, everyone, and thank you for attending this evening's presentation, whether in person or online. I'm disappointed that I'm not able to attend in person. I'm Alan Clayton, a member of the Toronto section for over 20 years, and I'm a former chair and current executive committee member of the section. The Toronto section is one of, if not the most active AES sections in the world. We hold monthly meetings from September through June, typically on the 3rd Thursday of each month. We also hold special events such as day-long presentations, manufacturers expositions, and tours of various facilities. I'd like to take a minute to remind you that when you join or renew your membership, you have the option of selecting a primary and 2 secondary sections. If you select Toronto as one of those, you will automatically receive our monthly meeting notices and invitations to special events. Remember, geographically, Toronto is the closest full section to Rochester. I'd like to thank all of our sponsors: Solotech, Gear Audio, Sonotechnique, Bell Media, BRTB, YSL Pro, Global USS, Electrosonics Canada, Adamson, Lao, avshop.ca, and Q5X. Thank you for sponsoring our section. Thank you to the University of Rochester student section for hosting this meeting, and thank you to Julie and Jason for making the trip to speak to us tonight. I'd like to give a special thanks to Kristen Barsahovsky and Jack Cunningham, who did all of the heavy lifting in my absence. Without their efforts, we wouldn't be having this meeting tonight. Once again, thank you all for attending. I think you're in for a special evening.
And on that note, we'd like to welcome our first presenter, Snyder.
All right, hopefully the wonderful Shure microphone will be working and you can hear me. So thank you so much to Kristen and Jack for all of your help in getting us from place to place and letting us know everything we need to know to be here to present to you this evening. So my topic is more of a look back on history and a little bit of an overview on what Shure does. So Ben Bauer and his place in Shure history. So first thing, I'll tell you a little bit about myself. I do not have an engineering background. My degree is pretty much in everything that is not engineering. I have been working at Shure for a little over 15 years. I started out as the librarian only, and I had the archives added to my duties about a year after I started. Some people ask me, do I have a favorite microphone? And for reasons that are a little challenging to explain, yes, I love that Hercules 510C. The industrial design somehow just speaks to me. It's really freaking cute. And those gloves are a little gross, for which I apologize. So the archives, the point of any archives really is to select, preserve, and make available, as you can see on the slide, historical documentary material of enduring value. What that means to each institution will be completely different, but the University of Rochester, I'm sure, has a wonderful archive and special collections. Any place that you go, it could be an academic institution or a museum or a historical society. Chances are they're going to have archival materials and their basic mission will be the same. For me, I try to keep 2 of every product we have ever made at Shure. I keep data sheets, technical specs, advertising, you name it. If it tells the company story, I would like to keep it in our collection. Digital objects are kind of a new challenge for all archives. Again, if you happen to find yourself in one, you may want to ask how they are managing foreign digital objects. This computer is great right now. If I create a file that I can open on it in 20 years, this computer isn't going to be here anymore. The file might be corrupted, and that might be the only copy of that advertisement that was ever made. So this is a problem that archives all over the world are dealing with. Not unique to Shure, but just something for you to consider in what you look at and also in what you may create in the future. So Shure, the company, was founded by SN. He is the kid in the middle in this photo. He's about 15 years old. Just raising his hand. He is with his brother Samuel and a friend of theirs. They had just built a radio from a kit because back then, if you wanted to listen, that's what you had to do, was build it yourself. They look pretty happy. So, I'm assuming the radio worked and everything. He had a lifelong interest in radio. He got his first amateur radio license when he was, I believe, about 13 years old. But when he went to college, he actually didn't study business. He didn't study engineering. He actually went to the University of Chicago and studied geography. This reflected his interest in the world around him. He loved to travel. He loved to study languages, linguistics. He collected stamps. He liked to take photos. He was a man of many interests. And when he graduated, his intention was to teach, but he was having a hard time finding a job. So his father and his uncle, they were in the wholesale business, had a big network of connections in the wholesale industry. So they tried to help young Mr. Shure get a job. And everyone his dad called pretty much said the same thing. We agree. Your son sounds wonderful. We would love to hire him, but we don't have a spot right now. So call back later. Mr. Shure wanted to work. His parents probably wanted him out of the house. So what he ended up doing was taking a loan from his father and starting his own company, the Shure Radio Company. It's coming up on our 100th anniversary soon. It's going to be pretty exciting once we figure out how exactly we would like to celebrate it. He started out at a one-room office in downtown Chicago. He sold radio kits because he loves radio, but pretty much anything related to radio went into the catalog. And sometimes things that weren't related to radio at all, like home furnishings and camping equipment. Pretty much anything to keep that catalog company going ended up in that catalog. So after a little while, Mr. Shure saw that radios were starting to come fully assembled, and he was looking for new things to add to his catalog because radio kits were not selling as well. So what he ended up doing was taking a walk around the city of Chicago, and he saw in a lot of radio stations that they were using the same microphone. This microphone here you see on the screen, made by a company called Ellis. And they were pretty close to Chicago, and they had a pretty good product, but they didn't have a very good distribution network. Whereas Mr. Shure had this great network and was looking for a new product to distribute. So he ended up distributing Ellis microphones, and that is how Shure got into the microphone business to begin with. So after a couple of years, and I think there may have been a lawsuit or two involved between Shure and Ellis, Mr. Shure thought, you know what, maybe we could build something better ourselves. So he hired some engineers, and we brought out our first microphone, the 33N, in 1932. Now, since then, we've made a couple more things. Our product portfolio has expanded to cover all kinds of microphones, listening products, mixers, software. You name it, it's probably in there somewhere if it's related to audio. I used to say we do everything except for speakers, but we sort of do speakers now, so it's pretty much everything. Even if you don't think you're all that familiar with Shure products, you're probably more familiar than you think. The first microphone I will talk about here is our venerable SM58. Now, Shure products, people have asked, well, is there any rhyme or reason to the name? What about the numbering system? And a lot of times, no, the answer is it's just kind of arbitrary, and it's what people are feeling that day, and that's what the product gets named. But in this case, SM stands for studio microphone. That is what this microphone was brought out for, studio use. This was an instance where we had to rely on our customers to help us kind of reconfigure our advertising a little bit. We know it did not stay in the studio now. It's the most popular vocal microphone in the world, but that is where it started out. The second microphone I will talk about is our Unidyne 55, which this one came out in 1939. And when it came out, it was pretty revolutionary for the way it looked, the way it sounded, the way it was built. And people loved it. It looked awesome. But as television started to become a little bit more popular, you have this giant side address microphone in front of your face on a TV camera. People ask, well, maybe you could tinker with it a little bit and make it a little bit smaller. So here is yet another instance where the naming scheme actually does make sense. The 55S came out in 1951, and that S just stands for small. So this microphone is Ben Bauer's most recognizable invention. So we're here to talk about not just Shure history, but also one of our most celebrated engineers at the company, Benjamin Bauer. So he is the engineer who is behind this microphone. It was the world's first cardioid microphone with a single dynamic element. Up until that point, microphones had multiple cartridges inside that had to be in perfect balance with each other, or the microphone would stop working. There were feedback problems. It was just a mess. So Ben Bauer, through his technical expertise, solved all of these problems and helped bring out this microphone. Now, this microphone was so well loved and appreciated that this advertisement you see on screen here came out with the 55S. And it doesn't say Shure anywhere on this ad, but the industrial design and the microphone itself were so well known at that time, it was still a really successful ad campaign. And Shure is pretty much making the same microphone today. So it's the outside looks exactly the same. The inside, we've made a couple of technical improvements, but we are still manufacturing and selling this product today, which I think is pretty amazing to have a very similar, if not the same product from 1939 still be a major part of our product portfolio. So Mr. Bauer, who was born Benjamin Baumschweiger, invented the Uniphase principle used in our Unidyne microphones, and he was only 24 years old when he created this innovative product. So he was just about to turn 25 in this photo. This was taken in 1938. This is a picture of sales representatives that were having a luncheon in downtown Chicago. He aged a little bit. Paperwork will do that to you. This was taken a couple of years later at his desk at Shure Brothers in Chicago. So of particular note about our Unidyne microphone, in 2014, we celebrated its 75th birthday, and we kicked off our year with an IEEE Milestone Award in Electrical Engineering and Computing. This is a really special award to us. You have to apply for it, and in your application, you have to show that your invention was of significant positive benefit to humanity. Now that's really broad, but IEEE wants submissions from all over the engineering world. So to give you an idea of the types of things that are granted this award, here are the other things that were granted awards from that same era. So you can see we are in some really incredible company. So why the Unidyne? What was so great other than that it looked really cool? It helps people communicate at a time when being able to communicate with large groups of people across a wide geographic spectrum was really important. When World War II was going on, the political situation was really volatile. So you wanted a reliable, low-cost, dependable microphone to help you communicate. And so that's where our Unidyne microphone came in, and that's the biggest reason why we were granted this particular award. So Ben Bauer was not originally from the United States. He had a long journey to get from Odessa, where he was born, to Chicago to create the Unidyne. So we'll talk a little bit about Bauer's history. So born Benjamin Baumschweiger, as I mentioned, he was born in Odessa on June 26th in 1913. Ongoing anti-Semitism and other related issues at the time led the family to leave Ukraine and head to London. They didn't stay in London for very long. They soon left, crossing the Atlantic to land in Havana, Cuba, which was a holding point for European Jews at the time. The United States at that point had a quota on Jews that it would let immigrate into the country, so they had to wait until they were allowed to enter the country. So in 1930, Ben left Havana to go to school in New York. He was only 17 years old, and he learned English while he was in school at Pratt. He stayed with relatives while he was living there and while he was going to school. And after he finished at age 19, he graduated from Pratt. He had a certificate in engineering, and he went to work for the Geralt radio company. Two-way radio at that point was a pretty new technology, so that's what he was involved with. Then at age 21, he decided he wanted to pursue a full-on bachelor's degree. So because Cincinnati had a large Jewish population, he had relatives there, and the University of Cincinnati had a co-op program that he could participate in. That is where he ended up in 1934. Here's a page of his class schedule, which I apologize might be a little bit challenging to read depending upon where you are sitting, but there's 20 hours of lab time per week for him. So he spent a lot of time in the lab, which perhaps some of you can identify with. So at that point, back in Chicago, SN Shure was looking for engineering interns. So he talked to his chief of engineering, a guy named Ralph Glover, and said, hey, can you see if you can dig up some interns for us? So Glover was a graduate of the University of Cincinnati. So that's the first place that he turned, was to his alma mater. And he wrote to a couple of professors there, and one of them wrote back to recommend junior Ben Baumschweiger as a co-op student. He is heading his class. So even as a junior, he was doing some really excellent work. So Glover very quickly wrote back, said, terrific, I'm so glad that you could find somebody. And the dates on these letters are all pretty close together. So Glover was really enthusiastic about this. And it sounds like Addison was also pretty excited to get one of his students into a co-op work program. I'm sure he will prove satisfactory. Well, there's an understatement for you, more than satisfactory. So he began his journey as a co-op student. He went between Chicago and Cincinnati starting in 1936, 8 weeks at a time. He would take the train between the two locations, made a whopping $15 per week. And when he graduated, he had a degree from the university in electrical engineering. He was officially hired full-time at Shure. $25 a week, which at that time was pretty good. So here he is, not quite looking as burdened by paperwork as he was in the photo I showed previously, having a meeting with our VP of personnel, our sales manager, and SN Shure, the president of the company. So development engineers then, now, and in the future are all required to keep lab notebooks where they're going to document all of their ideas that are potentially patentable. And we have a lot of engineering notebooks. But some of the earliest ones, the first 50 of them, they weren't in the building and we didn't quite know where they were. It's kind of a problem. They had to be somewhere. We just didn't know where. So we have a lot of Bauer's early work in the archives. We've got an article that's kind of a condensed version of the work that was what we thought was in his lab notebooks. Got a box with the prototypes for our Unidyne microphones. Probably one of the most valuable things in the collection to show the development from point A to the microphone as it came out in 1939. When we uncovered this in the archives, we were doing research for the 75th anniversary of the microphone. And this box had been in the archives for a while. There was no glass, there were no labels. The wood was pretty beat up, so we were a little confused as to what it was. But after we thought about it for a little while, we realized that these are likely the prototypes for this microphone, and we were pretty excited. So we've got some close-up photos here. You can see the first and second cartridge prototypes. You can see the third and the fourth. The third one is kind of an outlier. It's a little funny looking. What we discovered was that rather than fix a magnet to the prototype cartridge, only to discover that it's not in the right place, the distance is wrong, and have to start all over and use another magnet because magnets were kind of expensive back then. This was an adjustable electromagnet, so we could alter the distance, figure out where it needed to be relative to the rest of the cartridge before embarking on the next version of the prototype. And then we've got fifth and sixth, and you can see the vibration isolation on that left prototype. It's a little rough looking, but you get the idea. And then the final production version of the cartridge that was in the microphone as it came out in 1939. We have a carved wooden design prototype that we think was made around 1938. This was only uncovered in, we'll say, about 2000 when we were packing up to move to our current corporate headquarters location. We took apart our anechoic chamber in our old building, and there was this box under the floor of the chamber that was in it, and we have no idea who put it there, We don't know why they thought it was a safe space. I mean, we're really glad they saved it, but that's going to remain a mystery. You can see how it changed from this to the final version of the microphone. The orientation changed kind of from landscape to portrait, and the grill was brought all the way up to the top, but this is what it was going to look like at the beginning. We have the first production die casting for the Unidyne, so this doesn't have anything inside of it. It's just the metal housing and the silk windscreen. We have the front end of an Oldsmobile, which is not a microphone, but you can see that the design, perhaps we took our inspiration from things like Mr. Shure's car that he drove in the 1930s. We've got a copy of the patent for the conversion of wave motion into electrical energy. We have this first published white paper describing the Uniphase principle, and this was presented after the patent was granted. However, what we didn't have were lab notebooks 1 and 2. This is where offsite storage comes in. So around the time we dismantled the anechoic chamber to get everything from our old headquarters to move, I think people literally did a forearm sweep into banker's boxes of some of the desks in the building because the stuff in offsite storage is labeled with such things as miscellaneous files, which is really helpful when you're trying to figure out what's in the box when you're not actually at the storage site. So there are about 500 boxes of engineering-related documents in offsite storage. So we were feeling a little disheartened at the start of this project. We didn't really know what we were going to find. But the second box we pulled off the shelf happened to have Bauer's lab notebooks in it. My manager and I, who were there looking through these boxes at the time, we literally yelled and kind of scared the other people who worked in the facility, but we were really freaking excited. So what we found when we found Bauer's first 2 notebooks, inside the front cover of this one, dated September 4th, 1936. That was his first day as a co-op student. At this point, his name is still Baumsweiger. At a certain point in about 1941, he changed his name, and we think it was because Shure had a lot of contracts with the military at that point. Baumsweiger sounded very German, and it seems like such a ridiculous thing to change your name to Bauer, which doesn't, to my ears, sound really any less German, but apparently this made enough of a difference that Mr. Shure asked, and Ben said yes, he would do it. Also on here, you can see that Bauer's boss was Ralph Glover. Eventually, Bauer took his job, so be careful who you hire, I guess. So we've got this page here that is from his first day as a co-op student. Remember, English is his 4th language, so if you can read this, you can see that he had a really spectacular command of multiple languages. He has his note at the top saying, this work is mine and this work is no one else's, and he also had a critical note for his boss. On his first day, he was a confident guy, Ben Bauer, working on a heartbeat microphone. That was his very first assignment for the company. So May 27th, 1937, he is doing the math for a cosine and a cardioid microphone. The research that he did here kind of led to his development of the Uniphase principle. November 19th, he first describes the Uniphase principle. The following arrangement seems to offer possibilities. That is very true. Yes, it does. So when he was doing this research, he actually started out thinking about a crystal microphone. So when that Unidyne came out in 1939, it actually had a crystal microphone version that came out with it. Crystal microphones didn't quite have the same durability as a dynamic because that salt crystal inside would dissolve under adverse conditions like humidity. The stuff that Shure used was pretty durable for a crystal, but all the same, crystal microphones kind of were gradually phased out, and we really focused on dynamic instead. So although he started out looking at crystal microphones, that's not really where we stayed. So in January of 38, he started to observe that a moving coil design, a dynamic design, would have certain advantages over a ribbon microphone design. And those notebooks also explained why those first 2 prototypes in that box didn't exhibit a magnetic field. This was because you literally took a horseshoe magnet and held it up to the prototype to make it work. Because as I mentioned, magnets were really expensive. So he didn't want to attach something that he was only going to have to destroy to take it apart to go to the next version of his prototype. So we've got prototype 1 here, and then a drawing of prototype 2 with a magnet attached to the prototype. January 29th is the first mention of the now established 150 ohm standard used for low impedance microphones. Then in May, he started to do some additional work on the Uniphase network. And here he also begins using the term D for distance between the diaphragm front and the opening at the diaphragm rear. Also mentioned here is Hugh Knowles, who founded Knowles Electronics. He actually worked for Shure for a little while in the 30s and the 40s. So on May 18th, that diaphragm, voice coil, and magnetic structure begin to take their final form. Then in October, the patent was officially filed, conversion of wave motion into electrical energy. Now, if you can see on the top here, it talks about his analysis being performed in Key West, which is not Chicago, it is not Cincinnati, and it is not New York. That is actually where the woman who would become his wife lived. He met her on a ferry from Havana, and they kept in touch, and things worked out, and they ended up getting married. So at the time he was working on the Uniphase principle, that is not the only thing he is working on. He is working on a lot of other stuff. So May 22nd, he is doing some calculations for a controlled reluctance microphone, which is the same as a controlled magnetic microphone. These were very durable microphones, often used in adverse conditions, such as World War II. Here we have some discussion of a super directional microphones. This is one of the first instances where you talked about super to describe a microphone with a pattern that is tighter than a cardioid. Another term that was kind of thrown around at the time was ultracardioid, but ultimately supercardioid stuck, and that's the same term that we use today. So here we have in June 21st of 1938, Bauer talks about this new idea he has for beam type highly directional microphones. Took us a little while, but eventually we ended up actually acting on it and coming out with steerable ceiling arrays using much of the same math. So there were a lot of things that Bauer came up with, and other engineers at the same time came up with some really interesting calculations and interesting ideas. Some of the challenges weren't just that we couldn't figure out the math behind something. It was because we didn't have the materials. The physical materials didn't exist to bring some of these ideas to fruition until, say, 78 years later. So it's really interesting to look and see how much of what was thought about in the past ended up happening, but not happening until, now. So in addition to the discussion of directional microphones, he also graphed the calculated directional patterns, only did half of it because the other half's a mirror image, so he did not draw the other half. So what's in these notebooks? We have 300 pages in the first one. We have 195 pages in the second one. There's a lot of material. All of it has since been digitized. It has been indexed so that we can use it in-house to read and research and see what other inventions might be lurking in there that we have not thought about yet. So after all that, what happened to Ben Bauer? So in the 50s, he was working on a project with CBS Labs that was not secret to Shure and not secret to CBS, but secret to the rest of the world. CBS Labs was working on a stereo LP, a stereo record. And the concept was great, but if you wanted to play it, there were no stereo phono cartridges. So CBS Labs worked with Shure, who made a lot of phono cartridges at the time, to develop a stereo phono cartridge in tandem with the stereo record so they could be released together and everyone could buy a new phono cartridge and listen to these great new records. So that relationship worked out really well to the point where the president of CBS Labs ended up poaching Ben from Shure. He invited him to head the audio and acoustical research labs at CBS. This was a really great opportunity for Ben Bauer because, as sometimes happens when you rise through the ranks at a company, you do less research and more paperwork. And Bauer was not really a fan of paperwork. He was doing a lot of patent research and legal resolution, and that is not what he wanted to be doing. He wanted to be inventing. He wanted to be working on new projects. So this was an offer that he couldn't refuse. So he ended up leaving Shure and going to work for CBS Labs. Now, CBS had a rule that at 65, you had to retire. well, this rule applied to everybody except for the president because he didn't want to retire. But at 65 in 1978, Ben was pretty much forced into retirement. He had over 100 patents to his name at that point. And he, I guess, was a guy who really needed to work because it wasn't so long after he was forced to retire that he actually passed away from a heart attack. It's very unfortunate. In 2014, when we celebrated that anniversary for our Unidyne microphone and celebrated the IEEE award, we invited Bauer's two sons to Shure to take part in the event with us. And so, you know, they were there and they like to talk. So we asked, you know, tell us a little bit about your dad. What was he like? What was it like living with him? What was his greatest achievement? And what they said was that their father worked a lot on secret projects for the military. A lot of it's still classified. We may never know exactly what it is. But the thing that he counted as his greatest achievement was the invention of the sonobuoy, which isn't a microphone that we made at all. This is something that he worked on with the military, and it helped track the movement of enemy submarines. And to him, that was really the pinnacle of his career. Now, we like to think it was the Unidyne, but, you know, this is what his kid said, so we're going to have to believe him. Ultimately, it's going to take us years to appreciate all of the material that's just in those 2 lab notebooks from his first 8 years at the company. It's great to think that this material that is, you know, nearing 100 years old is still yielding new and exciting research projects for us at Shure. So with that, I have no idea what time it is. I don't know how long that was. I've had a lot of coffee today.
30 minutes.
Yes. All right. Any questions that I could take from the audience, either in person or whoever might be watching via Zoom or YouTube? Yeah, I think the gentleman in the back had his hand up first.
So my name is Eldridge Steele. I'm an MB major here. I heard you talk a lot about challenges and like limitations of back then with like materials and things. I was kind of wondering, how do you balance sensitivity and noise reduction in microphone designs today?
This may be a question that's better for Jason to answer. I don't know if you want to come up and answer or.
Let's get to the end of my presentation and we can do the technical stuff then if you want to.
Okay, hold on to that question and Jason will answer it after his presentation. Okay, yes.
The Shure, do you folks offer restoration services? I know you've got a really snazzy repair plan, and that's always been great.
Yes.
Unlike a lot of other manufacturers.
We appreciate
But
that.
is there actually restoration services for some of these older microphones if they show up in places? Is there someone there that knows how and where to do what needs to be done to make those authentic again?
Unofficially, people at the company might know how to do it, but on an official basis, it's not a service that we offer, but we can make recommendations depending on where you are geographically. We kind of have a network of people that we know do that kind of stuff. So if you have something and you're wondering about it, then you can send me an email at this address and we can see if we can connect you with someone who'd be able to help.
Thank you.
You're welcome. Questions from the audience? Yes.
We have a question on Zoom about just an overview of Shure's history with wireless microphones.
Mm-hmm. So, all right. Our first wireless microphone actually came out in 1953. So that wasn't just Shure's first wireless. It was the world's first commercially viable wireless system. It was called the Vagabond because you could wander around with it. It had 3 parts. You had a handheld transmitter, you had a receiver box, and you had a ring of copper wire that you would lay down on your stage floor. It would cover about 7 square feet. And it was a giant radio antenna. So if you stand inside your circle of wire, your microphone works wonderfully. The farther away you get from the center of your circle of wire, the less well your microphone works, which seems ridiculous by today's standards. But in 1953, this was like crazy technology that no one had seen before. We sold a lot of our early units to nightclubs in Las Vegas, which was just getting its start as a live entertainment destination. So it was a really good proving ground for the technology, but it was really expensive. Trying to think of the equivalent, say it was like around maybe $1,500 in today's dollars for the system, which I mean, that's kind of a lot. So it lasted in our catalog for a couple of years, but after that, sales weren't doing so wonderfully, and we decided we were just going to phase it out. In the late 1980s, that's when we got back into wireless in a big way, and we haven't really looked back since then. So much of our developments in that technology has been happening since the mid 80s. It's become a way more challenging landscape, of course, because bandwidth issues and arguing with various federal entities to try to figure out where we can operate and where we can't. And from the perspective of getting things certified in different countries, the rules for the US are one thing, the rules for Canada are an entirely different scenario. The rules for every country pretty much has its own rules. So the landscape has gotten more complicated, but at the same time, we've gotten better at targeting things to different markets. So I don't know if that answers the question. Yes.
So aside from the notebooks, was there anything else in the archive that was challenging to track down?
As far as things we know that we're missing, there are probably a whole slew of products from the 1930s that we may never find because so much was melted down as scrap for the war effort. So there's like some batteries and some stands and possibly some other microphones that we just don't know about, that we don't have. But I can't think of any other major thing that we're missing that we're really keeping an eye out for. My manager spends a lot of time on eBay. He has cultivated a lot of relationships with vintage microphone collectors globally. So we have people who are kind of keeping an eye out. And if they see something that they know is a bit of a rarity, they'll email us to ask, hey, is this something that you need for the collection? And a lot of times we have it, but sometimes we don't. So I'm not sure what we don't have, but when it comes up, we're going to jump on it. Welcome.
Another question from Zoom. Why did Shure end its long history of making world-class notebooks?
Sure. I knew this question was going to come up. So yes, Shure was known for a very long time for its phono cartridge production, and we did tone arms as well for quite a while. The equipment that we used to make the phono cartridges was literally the same equipment from about 1950 onward. And to call it steampunk would be generous. The companies that manufactured the equipment went out of business. So if we needed something to be repaired, it was always an ordeal. The people who made the phono cartridges, they weren't the same people from the 1950s, but they were people who had been working for Shure for a very long time. And what we discovered was we couldn't keep the equipment repaired up to our quality standards anymore. And the knowledge transfer from the people who were getting ready to retire on the phono line was really challenging, to the point where it became a quality issue. And we wanted to be able to stand behind the product, and we didn't feel like we were really able to do that anymore. So rather than make something that might end up being less than what we would expect from ourselves, we decided to exit the industry, which was really painful for a lot of people, both outside the company and inside the company. People were upset. I tried to rescue as much of the phono manufacturing line as I could reasonably fit into my archive, but that was only like 3 pieces because they're big. But we have some really great photos of all the manufacturing equipment. And I really wish I had a better answer, but I'm sorry. All right, if anyone else comes up with anything, I'll be here after the presentation, but I want to make sure that Jason has enough time to talk as well. So thank you all for listening. We'll bring you up into modern day.
Hello, everybody. My name is Jason. I am a senior acoustical engineer at Shure. I've been with the company about 5 years now, and I was asked to help present today on more of the more modern side, which Julie was talking about the past, and I'm talking about the present and future a little bit here. Yeah, let's get right into it. A little bit about me. I've been, like I said, I've been with Shure about 5 years, and I primarily work on condenser microphones and dynamic microphones. And we caught it early. You? Yes, I primarily work on the design of dynamic and condenser microphones. This also includes some R&D work on those subjects, manufacturing support. I have a degree in electrical engineering from Penn State and a master's degree in acoustics that I just completed this past winter. I was born and raised in the Pittsburgh area, and I'm a musician like a lot of other associates at Shure. It's not that big of a surprise that a company that makes audio equipment has a lot of musicians working there. A little bit about the group that I work in, the acoustical engineering group. We work in the main headquarters in Niles, Illinois, which is just north of Chicago. Our area we call the Mic Lab for reasons that probably should be obvious. We work on microphones, and it's our lab. Within the product development division, there's 15 engineers on our team of various technical backgrounds. It's honestly about a three-way even split between mechanical engineering, electrical engineering, and physics. So one thing I kind of wanted to go over today is a little bit more of like the reality of how do you take a microphone idea and the product at the end, how do you connect those two things? A lot of the time, especially I remember when I was in engineering school, you think to yourself, your design projects are all about like, here, I'm just making this one thing. I got to make one thing and I got to make sure I understand how it works. And at the end of the design class, you built that one thing and that was it. When you're trying to make something that you're going to sell thousands of and manufacture and send them all across the world, there's a lot more that goes into that. And I want to go over a little bit of that process of how we do it. And then at the end, go into some of the specifics of things we do in the manufacturing plant and how that is, unique to microphone design and unique to Shure. So the first phase of all this is research and development. Let's make one microphone. Let's make one of this thing that we want to do. And the first thing to think about at the beginning, because really when it comes down to it, engineering is all about one thing: trade-offs. So you think about getting some requirements from our marketing team, and you do a lot of trade-offs there to figure out what do you want, and you can take it at the expense of something else that maybe for this particular thing, you don't care that you're losing some of that. That's the reason there's so many different types of microphones. That's the reason there's so many different types of cars and just about anything else. There's trade-offs. You can't make a one-size-fits-all thing for everybody's application, everybody's tastes, everybody's purposes. So first thing when you're thinking about a new microphone, the two main types of microphones, dynamic and condenser mics, which I'm not going to go over too much. Basically, a dynamic mic is a speaker in reverse. It's got a magnet. It's got a coil attached to a diaphragm. That diaphragm moves the coil next to the magnet. You get a signal out of that. Condenser microphone is a electrical capacitor where one plate is able to move with the sound pressure. You get an electrical signal based off of that. And there's a lot of differences between those two that I won't get super into, but it heavily influences what type of microphone you want. There's some differences between those two. For the application that you're using it, the size can be very important. You can make, very large microphones. You can make very small microphones, especially condenser mics can get down to even about a 5 millimeter diameter size. When you're coming up with a new product, sometimes there's a discussion about make versus buy, because sometimes, most of the time, we're making the transducers in-house. Sometimes, especially for some of our lower tier products, it makes sense for us to buy something that's made by another supplier and then, add our spin to it. You think about the typical use cases. You think, well, is this going to be used as a vocal microphone? Is this going to be used on instruments? Is this going to be used on a specific type of instrument, like a kick drum or something that has some very specific parameters? Is this going to be used in the studio, or is this going to be used on the stage? Is it going to be used in both? And then you also consider, like, a good, better, best is usually what you want. You want something for entry level. You want something for kind of experienced people. And then you also want something for, the highest tier, the people selling out the stadiums, the people in the nicest recording studios around. You want to give something for everybody. And there's a lot of trade-offs you'll make to allow that to work for whichever price bracket and tier that you're looking for. The response of the microphone. What does it sound like? That's obviously a really important thing for microphones. Do you have a flat frequency response? Is it tailored for vocals? Is it specialized for something else, like a kick drum mic I mentioned earlier? That's got a very specialized frequency response, and you don't typically see a kick drum mic used on a ton of other things because of that. Polar pattern, how it picks up sound around it. You need a cardioid, do you need a supercardioid, bidirectional, omnidirectional? Each application kind of has its own different things. And these are all the things you need to consider at the beginning of how do I solve the problem of, we want this microphone for this thing. Let's see, next slide. Now I know what to build. Where do we start? Well, that's always kind of a difficult task to go from nothing to something. But nowadays, there's a lot of simulation tools that allow you to at least get a pretty good idea if your idea is going to work before you have to spend a lot of money to make a first few prototypes. A lot of microphone design can be done with electrical circuit analogs. So you can simulate those in conventional circuit design software and get a pretty good idea of how your microphone's going to work. There's some limitations to that. You're making a lot of assumptions about how things do work, but it can give you a good idea of the gist of your design if you're in the ballpark, if it's worth kind of going to the next level. There's a lot of other software packages out there that allow you to simulate things even more thoroughly, like ComSol. You can basically, you make a 3D model of everything and you apply physics to different parts. You say, oh, well, this is all air and here's all my boundaries. And you can solve that and give you some more information about it. Using existing parts and pieces for microphones that already exist, you don't have to start completely from scratch. If you know that a microphone we already make has a diaphragm that was already supplied, you can use that on the next one if it makes sense for your design. And, being able to 3D print or make prototypes in-house, we have a model shop at our headquarters that can, machine us up a lot of parts that we can build into a microphone real easy. And, being able to use that to try out some things that maybe it's too difficult to simulate, or if you've done enough simulation and you want to just make sure you did that simulation right, you always got to check and make sure you build the first one. Second phase, it's all about planning, which is maybe not the most interesting thing in the world, but you always have to do it. When you're trying to make a microphone that's going to go to production, that's going to be sold in large quantities, you got to really plan out how you get there. You can't just make one and then try and make another. And, you have to create a full bill of materials, make sure you know all the things that are going into the microphone. Mechanical engineering team makes some CAD models. You identify anything that you're reusing, see if you could save some money that way, stuff that's already proven out. You need to identify the suppliers that are going to be able to make all those parts for you. And especially at the prototype phase, sometimes you have a different supplier that makes you your prototype parts versus your production parts, just based off of the amount of money it costs to make those parts. Some suppliers can do them at scale, and some will only do that at scale. So you have to use a prototype supplier to vet out your design first. Some things are higher risk because they're a difficult or unique thing for this. It's not an off-the-shelf part or something that you just can easily machine or mold up in plastic. So you spend some time early on saying, like, what are we most worried about? And who can we talk to ease that worry, reduce that risk? A lot of the times your projects, your lead times of how long you can do stuff is pretty dependent on this planning and the parts you get. Because obviously you can't build without your parts. But if you have a part that's going to take, 6 months for the company you're working with to get that to you, you have to plan around that. At this point, you also start thinking about the manufacturing process and developing a plan of how you're actually going to put this microphone together. We have 2 manufacturing facilities at Shure. One is in Juarez, Mexico. I've been able to travel there several times, and that's where most of the work that I do directly with their manufacturing plant is. We also have another manufacturing plant in Suzhou, China. And between the 2, we've recently commonized a lot of things. We make a lot of things at both plants. But again, at this stage in the process, you're, getting your initial flow down. You're figuring out what you're going to need. How much space do you need at the plant? How many people are you going to need for the line? You work with the manufacturing engineer really early on to make sure that they're, prepared for this big project that's coming down the line. And then you create some timelines for your builds. Next phase we call a working model build. This is the first time where you're making a decent quantity of these microphones. They're not the full production version. They're not perfect, but you need to make a handful of them so you can see the variation. You can see how difficult it is to put them together. If there's any things you need to fix, validating like part by part aspects of the design. Some of these parts might be the final ones at this point, but most of them are probably still prototypes. It helps you figure out which machinery and fixturing and things that you need so that you can build these mics, and you get to try it out. And if it doesn't work, you can iterate and make sure that you get it there by the time you need to make more of them. You get to see your failure modes really easy when you try and build your first batch, because I guarantee you they're not all going to work the first time. You get to see what's something you need to monitor, something you need to understand, and how it may influence further development of the design, nitty-gritty details that you need to pay attention to that you didn't know you had to until something went wrong. Next phase, what we call design model. So this is the first time you take that down to the manufacturing plant and you build a pretty large quantity. Comparably, we were building tens of microphones before. Now we're building maybe hundreds of microphones. The design engineering team and the manufacturing engineering team work very closely together here. This is kind of like a trait, a handoff from the design engineers to the manufacturing engineers. The design team knows how it's supposed to work and what's supposed to go together. And then the manufacturing engineering team has to make sure that they're able to do that and do it the same way every time. At this point, hopefully most of your parts are off tool, which means, they're from the production tool that's making the parts. You have your bill of material all set. You have all the logistics behind it that go into it that allow you to be able to make this product. And the first few builds will show you some things that you may have overlooked and got wrong. You'll see some bottlenecks of like, oh, this operation took too long, or, this only works 75% of the time. We need to dial in our process a little bit more so that we make sure we get it better. And then you iterate there a couple times. You certainly don't do just one of these builds. You do multiple of them. You see what's going wrong, and each time you fix more and more till you get to a point where you're building microphones that not only pass the test limits of what you set, so it sounds the way you want it to, but also so they pass all your quality tests. Shure has a very strong history with quality and reliability, and is often recognized with its brand for being known for high quality, very durable microphones. Our standards are high. So when you make these units in a design model build, you have to make sure that they pass all of these tests before you would go into production, because you don't want to lose that standard there. We have a bunch of tests, including environmental tests, hot, cold storage, humidity, moisture resistance. We do some packaging testing to make sure that the products aren't going to be damaged during shipping or any of the packaging gets damaged. We do a drop test on all our microphones to make sure that they can survive the impact of someone dropping them or them falling off a table, anything like that. Things that are real use cases that a lot of other companies, their microphones aren't as durable, and you don't want to buy something if you know you're going to drop it and it's going to break. And then also cosmetic tests to make sure it is going to withstand chemicals or it being braided in some way. You'd like it to keep its original look as long as possible. Drop test is one of the unique tests, and it's designed to make sure the microphones can survive the harsh impact of a quick force of it falling down. We do 2 different types of tests there. We have hand drop and stand drop. The hand drop is done by an automated machine that's pictured there. You place the microphone in there, it lifts up, and then it just goes in free fall. And once it gets to the bottom, it releases it. So you can control the position, but it's repeatedly going, it's going in a free fall motion like it normally would. Both of these are about 6 feet from the floor, or exactly 6 feet from the floor. And they have to pass 10 total drops at different angles for it to meet our standards, which is an extremely challenging thing we've set for ourselves. Almost every new microphone project comes down to iterating on a design model build, because there's little things about how you designed the mounting of this microphone to make sure that it passes this. But to the customer, that can be a huge deal. There's a lot of shows that wouldn't have gone on had a microphone broken in the middle of the set because someone was, going too hard and it hits the floor, something like that. Reliability testing, moisture resistance. That's the harshest environmental test that we go through. Either drop or moisture resistance is usually what hangs you up, and you got to iterate a little bit on your design. This is a 10-day test where it sits in a test chamber that goes through various cycles of temperature, humidity, goes to extremely hot and very humid, down to very cold and very dry, and repeats that. And if a microphone could pass this test, a lot of our other environmental tests are subsets of this. But sometimes it's difficult when you have 10 days to see if it's going to pass or not. A lot of subtle little things in, the chemistry of how certain plastics interact with things and how you glue things together, and a bunch of subtleties like that have a heavy influence on this. But again, it's all about making sure that the customer has a microphone that they can trust in any environment. Once you've gotten through all that, into production, you're going to make thousands of these microphones, sell them everywhere. You do some ramp up builds, make sure you got everything you need for when you release to the public and say, hey, come buy this. Because usually if you got something new and you're excited about it, you hope that there's a lot of people that want to buy it immediately. And you want to make sure you can give everybody that wants to buy that first batch, you can supply it to them. Everything at that point is handled within the manufacturing plant in terms of demand planning and how the place orders so that they can produce enough to send to our distribution centers, and the distribution centers send it to either you can now buy direct, but also to Guitar Center or to Sweetwater, which I guess is another distribution center of this whole thing. All of our microphones go through an acoustic test 100% at the end of the line. And I'll go through a little more about that. And so the next part. Oh, that's right. I got a slide in here. Yeah, just mics are everywhere. This is a little test on pop culture for everybody. If you can name all six people that are in this, that means you know a little bit about pop culture from the 1960s till today. But microphone manufacturing. Here's a couple examples of unique manufacturing techniques and systems that we have in place in our plants. First thing that's relatively new and pretty modern is we have really advanced our serialization techniques, making sure that we can trace things from sub-assembly level into the full finished microphones and tracking the data. For a long time, we would be making microphones and we'd be testing it, and we'd see that we had 50 microphones tested that day. And if I wanted to pick one out for some particular reason, I would have to have all of those microphones sent, and then I would have to test them again and figure out which one was which. Obviously, that's not a very efficient way of doing it. And now we've modernized a lot. And you may see on some more newer models of things, you might notice a QR code in a small corner somewhere out of, like in this one, inside the XLR connector, trying to be hidden. That helps us a lot with tracing, and great for troubleshooting if there's issues in the production line, because then you can kind of trace this information back for when things happen. A lot of automated presses and glue robots. There's a lot of very precise actions that are done to put some parts together. Like this glue robot pictured there is putting glue around a diaphragm that's going to be glued to a coil for a dynamic mic. A lot of this used to be done by just highly trained workers on the line and years of experience. And that's great until, someone retires or someone's sick that day, something like that. And you want to be able to repeatedly make the same microphone every time. And now there's a lot of ways that You can do that with these glue robots that are very defined with their positioning. They put the exact amount of glue that you need. A lot of automated presses that allow you to see how much force exactly that you're pushing down on combining two parts for press fits or pressure sensitive adhesive to combine some things. And it really reduces your variation from microphone to microphone, which is another thing that ends up being good for the customer. Manometers. This is a really unique tool used for acoustic engineers. We use this a lot in development, but we also are actively using them in our production floor. There's a design parameter used in microphones called acoustical resistance. It's analogous to electrical resistance, where an electrical resistor, there's a voltage drop across the resistor. In acoustic resistance, there is a pressure drop across an acoustic resistor. It's much harder to measure that than just picking up a multimeter like you do for an electrical resistor, because you have to measure the pressure and the airflow to do that. And we have a bunch of cloths, meshes, metal parts with small arrays of holes that produce these resistances, and they have to be within our acceptable range or the microphone's not going to have the correct response. And so we have these all throughout the plant, and different flow rates to measure different values of resistances. Everything has to have its own test fixtures and everything. We have a computerized program now that some of these parts are serialized, and you scan the serial number of the part, you put it in the machine, you click the right program, push start, it saves the data. So then you can see all of the acoustic resistances to track if you have any problems, if you got a bad batch of a material from a supplier, or if you're doing some process earlier up in the line wrong. And you can catch all those things there before you build up a bunch of microphones that didn't work because you didn't see it here. Electrical resistance and capacitance testing. Condenser microphones, cartridges have a capacitance to them. It's relatively low in the picofarad range, but it's an extremely helpful thing that you can check to verify that you've put this together correctly. Because if the diaphragm got stuck and collapsed, you can see a very large change in that. You can also kind of get away from seeing if the back plate or the diaphragm's dished, or the back plate's warped a little bit, or there's some debris in there. You can kind of use the capacitance measurement to find your way to understanding some of those problems. And we track those digitally as well. Dynamic mics, the coil in there, you have an electrical resistance, and you measure that to make sure everything's connected and working well, and saving that data as well. Backplate charging. Condenser mics need to have a power source. The original condenser mics typically had an external power supply that provided a fixed voltage that would allow the mic to work, because without that fixed voltage, you're not going to be able to get your signal out. Electret microphones use what's called an electret, which is a fixed charge placed in a very thin membrane. And that goes on our back plates. And we have a charging system where basically you put the back plates in a little conveyor in a tray that is conductive, and it goes along this conveyor that's conductive. And so it's all grounded. And then you put it under an electric field that puts the charge on the back plates. And then in the same conveyor, there's a scanner to make sure that everything is the charge that you needed it to be. And our machine even can individually pick out bad parts with a little suction, goes and grabs the one and tosses it in the bad, good and bad bins there. Our condenser mic diaphragms we make in-house too. There is a large sheet of a very thin material used for the condenser mic diaphragms. It's a conductive material because it has to be to work properly, but it's a plastic with a thin layer of usually gold, sometimes nickel for a lower cost mic. You take this sheet, you tension it over this circular area where a vacuum sucks it down and it holds it at the tension that you want, just kind of like a drum head where you have to tension that properly. You have that same parameter here where you want to make sure that that diaphragm is vibrating in the way you want it to. We make those in a big batch where you tension one big ring and you have a bunch of the smaller rings that make the diaphragm. You put the glue onto those, you attach that to the tensioned membrane there. Take them out, you trim them, and then you have all those parts that you can measure individually to see the resonance frequency of those, which is again a design parameter that goes in for condenser mics. A magnetizer for the dynamic mics. Obviously, a magnet is the main source of energy that allows a dynamic mic to work. It would not be a good idea to be assembling things with an already magnetized magnet. So the full assembly is done on these, and then at the end, you're able to magnetize the material. Basically, it's just a really big coil and a really large capacitor that just puts one jolt of energy through the coil, and that polarizes the magnet. And then we have a little check station there where there's a little light. You place it on there and just make sure that everything's good. Two main different types of magnets. The older magnets are made of an alloy called alnico, which is, I believe, aluminum, nickel, cobalt. And then ever since the late 80s, early 90s, neodymium magnets are the most commonly used magnets nowadays because they have a much more energy density to them. These require different ways to do this, but the SM58 is old enough that it still uses an alnico magnet because that was designed in the 1960s and that was the best material at the time. And then some of our newer dynamic microphones, like the beta line, they all use neodymium magnets and different parameters of how you set that up. And the magnetizer allow you to do that. Acoustic testing. So every single microphone that we build in our plants goes through what we call close talk testing. Because doing an acoustic test, you're subject to the environment that you're in, and it's kind of hard to isolate without building a full anechoic chamber. You want to have a way to test every microphone reliably that doesn't require you going to this one big room that you had to set up. And close talk testing allows us to do that. When you place the microphone very close to the speaker, you're really doing the best you can to isolate it from outside noise. We place the microphones 1 centimeter away from these speakers. We do a sweep from 100 hertz to 10 kilohertz. And there's an electronic system, computerized system that has test limits in there. They'll tell you that it passed every single frequency limit or failed in an individual one. And it saves that data, and we can view it on an online server so we can see, here's a trend of all the mics that we built over the last couple of days. You look at all that data, you can see, we're starting to trend more low frequency. And then you can look into that and understand what's going on in case, we're about to go past our limits or we got something that's a little out of the ordinary. Having all that data traceability is really helpful. And also it ensures that every microphone that goes out of the plant meets the standard we set for how it's supposed to sound. Like I said, we can't do every single one in the big anechoic chamber, but we do a lot of audits on large production batches. Some more complicated or high-end microphones, we even do 100% in our anechoic chamber, which is a big chamber that has a bunch of sound absorbing wedges in it so that it's very quiet in there. In fact, our anechoic chambers in Niles, I believe, are some of the quietest rooms in the world. And it's pretty interesting to stand in there for a while. You don't really notice too much for the first few minutes, but if you stand in there for about 10, 15 minutes, your brain really does not know how to react to not hearing any sound. But when we do the testing in there, we place a mic about 2 feet from the speaker. Here we can test its off-axis performance. So the polar pattern and how it picks up sound at various angles. You can check that in here. There's a motorized mechanism that turns the microphone so you can see to what angle. And then just like with the close talk testing, all saved digitally, you have all these curves that you can look at if you need to go and check in and understand what's going on. We also do some vibration testing primarily on our dynamic microphones. They're subject to handling noise because the coil in a dynamic microphone is relatively heavy. And so when that microphone is just being moved, gravity and any other forces where it's moving it will move that coil, and that will produce a signal out that you don't want. And so that's a parameter that you try and design to with a dynamic mic to make sure that you can mitigate that as best as possible. And obviously, like any other of your design characteristics. If something goes wrong on the manufacturing line, you want to be able to test it to make sure you don't send out a bad product. And we do that with our dynamic mics here. We put them on a shaker, shake them between 20 hertz and 500 hertz. And just like the other systems, we got digital data acquisition and stored so we can, check that out. That's all I had prepared today. And I hope it was interesting. And then, anytime for questions, Julie and I are still here and we'll hopefully help to answer. Yep.
I had a question about the drop test.
Yeah.
Is that on all of your microphones?
Different microphones have slightly different parameters for it. All of our vocal microphones have that 6 foot requirement.
But like your ribbon might be held through different.
Our ribbon microphones pass that test.
Oh.
That is one of the features of the Shure ribbon mics, is that they are much more durable than most other ribbon mics, because there's a lot of boutique-y ribbon mics out there that sound great, but like you gotta have like a padded floor sometimes because if you take that thing, if that falls from 6 inches, sometimes you got to reposition the ribbon. But yes, our ribbon mics do have to pass those tests. So.
Going back to earlier when you're talking about like the playing phases and stuff.
Yeah.
I had 2 questions. So I was wondering just how long usually an average project can take and how many projects you might be working on at the same time. So I'm assuming it's not like one continuous project that you move on to the next.
It's a great question. How long it takes is usually longer than you expect. But I'm currently on a microphone project that is in its late design model phase, that we've been working on that formally as a full project for about 3 years. The R&D work for that predated that about an additional 5 years. There are a lot of other ones that, like, if you're doing some reusing, if you're reusing a lot of parts, it's not a completely new ground up design, that can be a lot quicker. Usually the quickest you're going to get everything from starting a project to being out there is a year and a half, at least the way that, with all of our rigorous quality standards and the way we want to make sure we're doing it, it can take a lot of time. And working on different projects at once, I personally am on one project that is at that stage, like I said, in design model stage. I'm on another project that is just starting out in the first couple stages. So we've done most of the R&D work for. We're now getting it to productize. And then the rest of my time is spent doing what we call maintenance line work, which is working directly with the manufacturing plant to solve any of their issues. I'm currently working on a project where we're dual sourcing our shock mount parts, which is not super interesting, but someone needs to do it because those rubber parts in the dynamic microphones help with the handling noise. And it's a very specific thing that you can't just use any rubber and get there and work. So, I would say most of our engineers in the acoustics group, 2 to 4 projects thereabouts. And usually if it works out right, they're in different phases. So they kind of all fade in and out of, I'm spending this week, I got to do a lot of stuff for this. And then that project is kind of, someone else has to do their part. And then hopefully your other project falls in. Doesn't quite always work like that, but that's the goal.
So probably a common question. What's the real difference between a 58 and a 57?
Just the grill. That's it. Everything else in there is the exact same. Yeah. So.
That's popular is going through the counterfeiting loss problem. Yeah. Is there a way, without having one to show us visuals up there, is there a way to actually tell a counterfeit 58 from that of one that you've actually manufactured? Because I tell my students, like, don't buy from an outlet built source.
Yeah.
And some of them don't hear me because they see $60 and think that's a steal. And I say, well, now you listen to it and use it, and 3 months from now and it doesn't work. It's like, I told you so. But is there something that is real obvious or something to look for? Like you had mentioned something about some little codes and things you're hiding in the XLRs and stuff. Is there something more obvious than that?
Yeah, I would say the thing that for SM58s and our dynamic mics specifically, most counterfeiters don't get the handling noise mitigation right. So if you were to pick up a real SM58 and the counterfeit one, you kind of shake them around a little bit, you'll be able to hear the difference in the counterfeit one, because that's how we do that's kind of a secret sauce that we've managed to keep secret and over all these years. Fortunately, otherwise they have gotten pretty good at some of the other things, but that is the gist of it though, is it's really easy to buy it directly from a reputable source now. And that is the recommendation, because there is a lot of counterfeiters out there. And that's happened once or twice, where there was one time we were sent a microphone to the lab that they were investigating to figure out if this was a counterfeit or not, because it looked so good. It turns out it was just someone from our manufacturing plant had like stolen it and sold it on a secondary market. But we had to go through and we were like, geez, these guys are really good. They even got the date codes on the PCB right. And then we realized that was it. So that's.
When you guys are designing prototypes, like what are like the most common problems that you guys see like during testing?
So what happens a lot at the beginning is, because a lot of these operations, like for a dynamic microphone, for instance, putting the coil and the diaphragm and lining it up right usually requires a lot of fixturing that you develop over the course of the project. A lot of the things you figure out at first that go wrong are that I don't have the refined motor skills to put this together like a trained someone on the line, or, you know, a very well developed test fixture and everything can do. So a lot of the failures at first are usually as a result of not having good enough parts yet, or not having your process defined, which is tricky then, because that's not all the things that could go wrong. And so you have to figure out, all right, if in our working model build, if we built 50 microphones and, you know, 15 of them didn't work right, was that because I'm not that great at building them? Or was that because something inherently in the design has this variation we don't like? And that can get really tricky, and you got to dive into very specific things. On the project that I'm on, the earlier builds, it was mostly, we couldn't get a bunch of parts from a real supplier in time, so we had to 3D print something. The tolerances of the 3D printer weren't good enough to do what we wanted. And so some of those parts were just out of spec, and it made the mic sound different. So it's tricky and kind of case by case, but that's why you got to do so many builds. You got to iterate so much. Is you know, you don't want to just jump to the finish line and then try and figure all this stuff out. You kind of slowly learn all that could go wrong until you've hopefully fixed all of it.
Yeah, you mentioned about the testing of the microphone frequency response, and the signal will output from the speaker. But what I'm thinking about is the speaker also has its own frequency response. So how can we eliminate the effect of that?
The software that we use to do that testing has calibration that equalizes the speaker like that. So that's like a regular maintenance thing we have to do in all the test systems is go through and calibrate that, because those speakers will drift with temperature and other things, very small amounts. But our test engineering department, that's like regular maintenance they do in the plant to make sure that all of those are calibrated properly, and it's kind of built into the test system, basically.
Just a personal question. Is there ever been a time where like you've worked on a project and you've actually put some time into it, but then after a while you realize like the feasibility of it just wouldn't work out, so you had to give up? Or
wasn't me giving up.
Yeah, I'm saying like
Yeah.
just saying in general.
Yeah, that happens sometimes. You can get to a point in a project, and then sometimes market factors change and the company realizes, well, I don't know if we'd be able to sell this, especially like if over the course of the project you don't keep the cost down that much. And then it's like, well, we could have sold it if you could make it for $50, but your design you guys have is like $75, so we don't know if we can sell it for that. That kind of evolves, you know, for a bunch of different ways. But that's one thing that's disheartening sometimes, is you can work a while on something and it doesn't make it to the finish line. I've actually, in my 5 years there, I primarily at the beginning focused on a lot of maintenance of line and some R&D work, but I've actually only had one thing that I've worked on fully been released at this point. So I'm really excited about the other thing I've been working on because that'll be the second thing in a much bigger project. So, do we have any online questions?
Yeah, Anthony in Toronto wants to know, will there ever be an IP audio, i.e. AES 67, network to PoE type studio microphone?
Well, maybe. I don't know if there's a demand for that. I don't specifically know. I'm not working on that project if that project's going on. Because I primarily work on all the XLR microphones. But I know that we're obviously doing a lot of networked audio for conferencing systems and a lot of microphones like that. And there's also a lot of work recently is using those microphones that were intended for conference applications or a bunch of other applications. And some of them could be used in the studio. A lot of the digital processing of microphones, you typically have MEMS microphones as the actual transducer that's used in that. And there's some inherent limitations to those. Usually they're not very good at handling high sound pressure levels. So making a digital microphone that kind of works studio quality is a really, really difficult thing to do. Hope that kind of answers the question. Anybody else?
I remember somebody a few years ago, somebody from Shure telling me that White House Communications bought 457s or something over the years, and only 3 have ever failed. It was one of your people. I just can't remember who it was.
It was probably my boss,
Very interesting.
Michael Pedersen.
Sounds right.
Yeah, it's gonna be fun.
Question. It seems that you folks have always marketed that combination, even though the SM started as a studio microphone. The 58 was always seemed to have been marketed as a vocal mic, 57 as an instrument mic. Curious as to why they would buy 400 of the 57s with the A2 windscreen as opposed to the vocal version of that to use for what it is they're using them for. Because it's always vocals, it's always spoken word.
To be honest, I'm not quite sure, but my best guess would be they always have the 2 of them side by side. And because it's the same other than that grill, you can put 2 of those closer and in a more compact and better looking state than 258s. Is for the redundancy, or they're having those 2 signals sent somewhere else. That would be my guess as to why they picked 57 instead of 58. Because performance wise, they're really the only difference is the 57, you can get closer to it, but in that application, it's on a podium. So it was probably the aesthetics between the 2.
Seems good to me.
Yeah. All right. If there are no more questions, I think we'll be hanging around for a little bit if there's any other things you want to bring up. But thanks for having us, and I hope you guys enjoyed the presentations.
Bring stickers if anybody would like some. And I also have information on our internship program, which I don't know if we have much in the way of openings for this coming summer, but if any of you are going to be wrapping up your sophomore year, then next summer, it's a possibility. So if you have questions about that or about working at Shure, then please come and talk to us as well.
I don't have another question. Yeah.
So that mic's been around for so long. That has been one continuous cost reduction effort. Not the exact same as it was 50 years ago in terms of